Welcome back to module 2. We are continuing with the meaning of probability distribution, and then we have presented how to normalize a wave function at t equals 0 in the initial time, and then we will try to find out what will happen to the total probability distribution over time in the quantum dynamics. That's exactly what we are trying to find out. Now here I would like to emphasize one more point here, is that it is interesting to observe that this function we have been able to normalize, but it is not necessary that all function can be normalized. And one important requirement of quantum dynamics or quantum mechanics is that only those function which can be normalized is acceptable in quantum mechanics. So we have to be careful, and in the next module we will find out the consequences of it. So what we have observed here is that I may begin with a normalized wave function like this. This is just an example. Why I need normalized wave function? Because only normalized wave function can give me statistical interpretation. If the statistical interpretation based on which the entire quantum mechanics has been built, if that interpretation fails, then there is no meaning of quantum mechanics anymore. That's why I have to begin with a normalized wave function in quantum dynamics. Second question is that, before we get into the second question, I will write down what is acceptable wave function in quantum mechanics. Acceptable wave function psi x, a particle will be represented by this wave function, and psi xt will be considered as physically acceptable wave function, or physically acceptable wave function is also called well behaved wave function in quantum mechanics, if and only if psi star psi must be single valued. It has to be single valued, which means that if I plot this rho, this is nothing but the rho density, if I plot it for a particular position, I should have only one value, not numerical one value, it is a single value. For this position, if I have two different values, it means that I cannot accept the wave function. The wave function which will give me a density where density I can have two different values for a particular position, then that wave function cannot be accepted. A density has to be only single valued. For a particular position, I have only one probability. I cannot have two different probabilities for a particular position. For a particular position, if I try to find out, okay, what is the probability of finding the particle at this position, I have only single answer to this question. Second one is that not infinite over a finite range. This is also important. Wave function cannot be infinite. The value of the wave function cannot be infinite. Continuous everywhere. Which means I cannot have a wave function which is like this, and then there is a discontinuation and then suddenly starting like this. So this wave function cannot be accepted as acceptable wave function in quantum mechanics. Continuous first derivative, it should possess continuous its first derivative should exist and it has to be continuous. And the last point is it must be normalizable. A wave function does not need to be in the normalized form. We can normalize it with the help of this equation, minus infinity to plus infinity. You integrate this one, it has to be 1. Total probability of finding the particle in the entire space is going to be 1, because I am dealing with only one particle. It is cloudy, that's why I cannot precisely tell where the particle is. I can have a distribution of possible position, that's all. So these are the characteristics of the wave function which I can accept as a possible solution in quantum mechanics. Our next concern, I told you that I have been able to normalize this wave function. At t equals 0, I have normalized it, and then particle will evolve as a function of t. That's all about dynamics. It will dynamically evolve. When it is dynamically evolving, my question is, what will happen to the total probability of the particle in the entire space? What will happen to this integration if I take time derivative of it? And it has to be 0 to preserve the normalization constant, or to preserve the global probability. Global probability is the entire space I am calculating, that's why it is called global probability. So global probability has to be maintained, it cannot change as a function of time. That's one important requirement of quantum dynamics, and that's I'm going to prove here. So once this psi xt at t equals 0 is normalized, it remains normalized at any later time. This is the proof we are going to do. This is a remarkable property of the TDSE, that it automatically preserves the normalization of the wave function, because always we will be using TDSE, time dependent Schrodinger equation, and when we plug this in, this t equals 0 wave function into TDSE, we should have this TDSE should not change the total probability distribution, or it should preserve the global global probability. So how to prove that? We will begin with this first derivative of the probability distribution function. We are taking with respect to time, and we are going to prove that with respect to time it should not change. That's why it is constant in time. Total probability is constant. So we will start with this derivative with respect to t. We are taking partial derivative here because psi is a function of x and t. There are two different variables. That's why you are considering partial derivative. And the way we can do that is just simple product rule. Of the derivative operator. On the other hand, from TDSE we can write down I h cut psi xt equals minus h cuts by 2m. This is the kinetic energy operator plus potential energy operator. Potential energy we are considering time independent, that's why we have space dependent component. We will for a while will be continuously using this time independent potential. So this is TDSE, and we just reorganize this TDSE a little bit. We get psi xt. The reason why we are considering, because here as you can see this is the derivative we have, time derivative of the wave function. So that's why we have to calculate, and these derivatives can be calculated from TDSE. So I reorganize it and I get I h cut by 2m psi xt minus I'm just writing v is a function of x, but I'm just writing v psi xt. So here what I have done, I will get, once I take this term on this side, on the right hand side, I get 1 by I h cut, and then I multiply like this way. This I multiplied by I get minus 1, and that's why we get this factor. So this is one a part of TDSE. Then we will consider the complex conjugate. Complex conjugate of the above equation. This is a function of xt equals complex conjugates. That's why I get minus sign. This is also complex conjugate. This is going to be plus IV. So all you'd like to do is that we insert this one here and we insert this one here. If we do that, then I can write down this part to be minus I h cut by 2m psi star plus IV h cut psi star into psi plus psi star to I h cut by 2m minus IV by h cut psi. What we see here is that this term and this term will cancel each other, and in the end I will write down this part first, which is I h cut by 2m psi star minus psi, and this can be again simplified as I h cut by 2m. This is first derivative psi star psi. I can write down, because if I consider the product rule one more time, this I can write down because one can take the first derivative first, psi star x, then the second derivative Then again here also the first derivative and the second derivative. So what we see is that this part cancel out and remaining part is going to be this one. That's why we can write down this first derivative. Once we have reduced the equation to this, one can now integrate it. This is what we have got from the first derivative with respect to time, and I'm going to now integrate both sides. If I integrate both sides, minus infinity to plus infinity, then I get integration of this, and integration of this is very easily can be obtained as 2m psi star minus psi. This is minus infinity to plus infinity. This is the limit we have, and this part is going to be 0. The reason why this part has to be 0 is because every well-behaved wave function has to be 0 at the infinity. So when psi star will be 0 at infinity, psi would be 0 at infinity. So in the end, this part is going to be 0. That's the basic assumption we have made. Every wave function which we consider in quantum mechanics, acceptable wave function which will be used in quantum mechanics, that has to be 0 at the infinity. That's the nature of the well-behaved wave function, and also that's the requirement comes from the square integration. Every wave function which can be used in quantum mechanics has to be square integrable. So this part is 0, but on the other hand, if I consider this part, because it's a time derivative and integration is with respect to space, I can take out the derivative out of this integration, and I can write down minus infinity to plus infinity psi xt dx is 0. Note that this is partial derivative because it is acting on this function. But after the integration, I do not get any space dependence. This is going to be constant value. It doesn't have space dependency because we are integrating the interspace. That's why it is going to be the total derivative. This is not a partial derivative anymore. So what we have proved right now is that the total probability is going to be always constant over the entire space. So a generic view of quantum dynamics is following: at t equals 0, I have some probability distribution, that is rho xt. At t equals t1 time, I have in another probability distribution. Probability distribution should change, otherwise there is no quantum dynamics. At t equals t3, again probability distribution should change, and that's the way quantum dynamics will evolve always. As a function of time, its distribution, the function which is representing possible position for the particle is changing. But if I continuously integrate from minus infinity to plus infinity, if I integrate the entire function is going to be 1 because I have only one particle in the entire space. Here also if I integrate it is going to be 1. Here also if I integrate it is going to be 1 as long as I start with a normalized wave function. So what we have proved is that TDSE is an equation which will naturally preserve this normalization constant or the global probability. It will preserve the global probability of the particle. The analysis which we have done so far is based on two postulates of quantum mechanics. Postulates are some hypotheses based on which the entire quantum mechanics subject has been built. And traditionally when we start studying quantum mechanics, we actually present the postulates first to understand the basic hypothesis based on which quantum mechanics will be built. But in this class we are not following that traditional method. We are presenting it, and whenever necessary we are mentioning that this comes from a few postulates of quantum mechanics. So whatever discussion we had so far, they are based on two postulates of quantum mechanics, and I am going to write down those postulates. It's good to know or remember this hypothesis of quantum mechanics. The state of a quantum particle is completely defined by its position and time dependent wave function that is represented by psi xt on one dimension. At time t, psi star psi is representing probability psi star psi multiplied by dx. So this part, this product gives the probability of finding a particle in the dx interval between x and x plus dx positions. Only a well behaved wave function represents a physically realizable state of the particle. A well-behaved wave function A well-behaved wave function must be normalizable and its first derivative must be continuous and finite. Once a wave function is normalized, it remains normalized at any later time if we use TDSE. This is a remarkable property of TDSE, time dependent Schrodinger equation, that it preserves the normalization constant. And we should mention that this is not only postulates of quantum mechanics, this is the consequence of that postulate also, because the last one is not a postulate anymore, we have proved it. So, there are consequences also we are writing. Okay. Postulate 2 and consequences we will write down here. The wave function of a particle evolves in time according to the time dependent Schrodinger equation that's called TDSE, has a simple form we have already used this postulate and we have seen two important concepts. A stationary state, this is something which we have learned in the previous module. A stationary state and superposition state. So, these are the consequences we have seen when we did the variable separation method. So, it is a good idea to see those postulates of quantum mechanics which we study in standard quantum mechanics class from a time dependent point of view. We will move forward and we will now look at the generic view of one dimensional motion of a particle which we can construct. The probability density distribution changes as a function of time when the quantum particle moves in space. That is something which we have clarified in many times. each distribution, this is exactly what we are showing here. We are showing that the probability density distribution is changing as a function of time in this three-dimensional plot. And we see that at different time distribution is changing. It is not necessary that distribution should change in the following way only. This is the only way distribution can change. Distribution can change in all possible ways. This is just one example which will clarify many important thing here. Each distribution can be experimentally obtained by performing many repeated measurements of the position of the particle at that given time. So what does it mean? It means that at t equals 0 time, I have to perform many measurements and then count how many counts I have for a particular position, and I'll be able to get a distribution function, and that distribution function is presented here. So each distribution function presented at different time, they are actually collection of, let's say, Avogadro number of repeated experiments which has been performed. At t equals t1, again we have to perform Avogadro number of experiments, and then we will get a distribution function. At t equals 2, t equals 3, and so on. That's the way we will move forward. And in module, as I mentioned before, that this kind of motion of a free particle we'll discuss in module 3. Right now we are not discussing it, so mathematical derivation will be done in module 3. I'll show you. But one thing is already clear here is that due to delocalized or global nature of a function which is represented by the particle, construction of a trajectory to describe the motion of a particle is not straightforward in quantum mechanics, because always there is a distribution of the particle. In classical mechanics, when you think about the classical mechanics or daily life, when I say that a flight is flying from Bangalore to Kolkata, we know every position of that flight at different time, and that's the precise information we always have, we always carry when you think about classical life, classical motion of a particle. That's exactly which has been shown here in this figure. A particle is moving and its position as a function of time has been shown. Every time, for any time, I know its exact position of the particle. So at this point, at this position, the particle position is here. At this time, the particle position is here. At this time, the particle position is here. Everything is known. So as a result, because we know everything, all point by point information is known, we can very easily construct a trajectory. Trajectory is nothing but flight path taken by the particle while flying or while moving. That's called trajectory. And anytime, for any classical system, we can create that trajectory. Question is, can I create similar kind of trajectory in quantum mechanics? Directly, no, it is not possible. It is not possible because I do not know exact precise position of the particle. Particle can be here, particle can be here, particle can be here, anywhere particle can be, and different experimental measurement will unravel the position in different position. So because we are dealing with a global wave function, it is not possible to directly construct the trajectory. However, which means that I do not have local information in quantum mechanics. However, there are 3 theorems which can provide the concept of trajectory in quantum dynamics. So what is the target, next target we have is that we are starting with a wave function which is global in nature, which is delocalized in nature. We will transform this wave function through these theorems to get local information, and once we get the local information, we will be able to construct trajectories. So, what kind of trajectories we will be able to construct in quantum dynamics? That is exactly what we are going to study in the next class. We will meet again.